All right. Hello, everyone. Welcome back to Comp 2160 Programming Practices. I hope that you all had a good weekend. The weather has finally been like sort of nice out, so it's nice to get out and actually be outside. It's nice to get out and be outside and not be like getting rained on all the time. So that was delightful. I hope that you all had a good weekend. This is the last week of the course. Hooray! Yeah, it's the last week of the course. Hold your applause until the end of the course. It's the last week of the course. This is, as with the rest of the weeks in this course, this is like 2 weeks of content, but it's the last week of this course. So I'm looking forward to that. I'm sure that you are all also looking forward to that. Today, I want to start immediately by checking in to see if there's any questions about assignment 3 after the weekend. And I'd also like to spend some time taking a look at the test suites that I've published on the course webpage for you to use for your own implementations. So just as a quick reminder, you're writing your own test suites, and these ones are test suites that I've produced for you. You're welcome to look at the test suites that I produced and use them as inspiration in some cases, but you're also building your own separate test suites for this. So we'll take a look at those after I give some time for questions. So are there any questions about assignment 3 so far? All right, I was expecting this to take 10 minutes. If there's no questions, that's great. Yeah.
Assignment 3 is pretty much just like, if you did question 1 and 2 properly, your stuff should hopefully pass those tests.
If you have put together a comprehensive test suite, then I'd expect that your code would pass mine. There's one where I am compiling your code with dn debug, so I'm turning assertions off and I'm running tests that violate assumptions, that explicitly violate contracts. And my goal here is to try and exercise your defensive programming. So you're asserting a bunch of stuff, but then you should also have conditional statements that prevent seg faults from happening. So that's the one that would probably catch people up. Yeah, but otherwise, if you've written a comprehensive test suite, then it should be smooth sailing. Yeah.
If when you're programming, you're not utilizing and debug, like just display always conditional statements, and like you have some to do with like you're not particularly.
Well, so assertions themselves are going to get turned off with ndebug. So when you compile your code with that ndebug flag, dndebug, whatever assertions were there, they're going to get replaced with that void 0 statement, and so they're going to do nothing basically. And that's kind of what I'm trying to make sure, is that if you have both an assertion that's testing to make sure that something's not equal to null upon entry, even when I compile it for release without those assertions turned on, I shouldn't get a seg fault when I run the code. Yeah.
Do we need to test the destroy zone function at all? Because there isn't really didn't really return anything, so I wasn't sure how.
The way that we're testing destroy zone, in at least the way that I'm testing your destroy zone, is with Valgrind. So I have, and again, I'll take a look at what I've posted for you, but in all of the test cases that I posted for you, I've also posted what my Valgrind output is. It's not inside the test suite. It's going to be verified by external tools in this case. Yeah. I mean, you should call destroy zone in your functions, and then you should be able to run Valgrind and see that there's no leaks, like there's nothing left behind that has been allocated by malloc. But there's no way, given the interface, for you to check and see if zone destroy has actually done anything.
Well, on top of that as well, do we need to test the like dump function as well, or
the dump function is for information, and the expected format is what's in this test suite. So you can see what all of my outputs are. I've included both the expected output from each test suite and the expected output from Valgrind. So your ZDump function can produce the exact same output that I'm producing. The graders aren't looking to see what it actually produces. It's just there to see, like, does it actually have the metadata that we're expecting? The format doesn't have to be identical to what I've got. That's what I'm trying to say. Yeah. Yeah.
The main zones.c file, should that contain a test?
The main zones.c file should just contain your zone implementation. There should be no main function in it. And then what you will be doing is making a separate file that's called main or test or test zones or something that will actually have the main function that will have all of your test suites in it. The zones.c file, that one would be the one where your test suite is. Okay. Yeah.
Can we expect assignment 2 grades back before this one's due?
Yes. The question is, can we expect to get assignment 2 grades back before this one's due? You should. I've asked the graders to give me feedback by Wednesday this week. So it's not a lot of time before the assignment's due, but there's some time before the assignment's due. Yeah. Again, my cursory look at submissions for assignment 2, the main things to note are don't use assert in your tests. The test suite themselves should just be conditional statements, and that's explicitly because one of my tests turns all of your assertions off. So if all your assertions are turned off, then your tests aren't going to do anything. So, and then the other thing, that's the main thing. You know, the other thing is best practices. Many of the random sampling that I looked at had multiple exit points for a function. So make sure that you only have one return statement, for example, in your code. Use curly braces around single statement, conditional statement, that sort of thing. Yeah.
And just to make sure that it doesn't have to be like the best practices.
No, the test suite explicitly does not have best practices or programming standards as an assessment. The test suite is all about the data that you're producing. So we're looking really just for edge cases and general cases as opposed to a well-functioning, well-designed test suite. Yeah.
So to make zone, when we're making the zone, are we going to initialize every point in the same place or something, or we're just going to leave it?
So when you're calling make zone, the result of make zone in terms of your linked list structure should be that your linked list is still just pointing at null. It should be empty because there haven't been any allocations yet. You could, I guess, like pre-allocate your entire list and have a single pointer at every single byte in the zone, but that would be kind of a lot of room for error there because you're going to have a lot of extra allocations that are done for maybe nothing. The better strategy is you'll allocate nodes to your list when zalloc is called. So make zone itself should initialize the zone, but the list of allocations should probably stay empty at that point. Yeah.
In the blocks, so my understanding is that if the block that you're drawing from the block points the address in zones of where that block sits.
I'm just going to pull this up and then we can all maybe see and talk about the same thing. There we go.
Yeah, so like it's set 7 and then block points to the start of Kraken. So
Yeah.
basically block is the address of 0.
Yeah.
And then for the next block, it's the address of index 8.
That's right.
Okay.
Yeah.
Yeah.
Okay. All right. Okay, cool. Yeah. Yes.
So when using Valgrind, I noticed that like my code would like be memory safe, and it would say like there's no leaks, but it would show a bunch of like warnings that don't show when I like compile or run it. do we have to worry about like those kind of things, or just the memory and stuff?
The only warnings that we care about are from Clang itself. The report in Valgrind should say no leaks possible. That's what I'm looking for. That's what the graders are going to look for when they run Valgrind on your code is no leaks possible. One of the tests that I'm giving, it is filled with warnings. There's even leaks in one of the tests that I'm giving you, but it's not from our code. It's from code that we're using in an external library. Yeah. So we're not really too concerned about warnings. We're more concerned about all of the bytes that were allocated with malloc have been released with free, and that there's that statement of no leaks possible at the bottom of the report. Any other questions? Okay. I'm going to take a look at the testing suite that I've produced for you. So there's 5 tests, and there's a README file as always. There's actually a README file in each one of these directories for the tests that are there. So the README file will describe approximately what the test does, and it will describe how you should compile it and what the general expectations are for this. One of the things that you're going to see when you go into each of these directories is that there's no zones.c file, but there is a zones.h. So my test.c file includes zones.h, but you have to put your own zones.c into this before it will work. If I try to compile this right now with make, there's no zones.c to make zones.o, so it's not going to compile anything. I'm going to recommend that, one, you could just copy the file into each of these directories, but what you may find is that as you're going through the tests, you're going to be making changes to zones.c so that it passes the tests that I've given to you. So copying is reasonable, but if you copy it, you're making a copy of it. So in each of the different test directories, you're going to have a different copy of zones.c. I'm going to recommend that you use a different tool instead, and that tool is called ln. ln here is a tool that will make links between files, and I'm specifically suggesting that you should make a soft link. This is kind of like a shortcut. So if I do ln-s here, what that does is it will make a soft link to a file. It'll make a shortcut to a file. And so when it appears in this directory, I'll do this right now. So I'm going to say ln-s, and I'm going to link to my version of zones.c. This says, please make a link to this file in this current directory. So I want to make a soft link to back to 2 directories, and then a folder called solution, and then a file called zones.c. When I list the contents of this directory, you'll see now that there is a file that's called zones.c here. There is this file, and it's got this special arrow that says it's pointing at this actual file. If I make changes to this, I'm not going to open it here, but if I make, I'm not going to open it here. If I make changes to this file, it's making changes to the thing that it's pointing at. It's not making changes to a file that's in this directory. This is just a shortcut. But there's now a file called zones.c, and I can make this. So now it will go through the process of compiling it, and it will produce the output that I'm doing. So when you're working with this, in each of these test directories, I'm going to do this as we step through them. I'm going to suggest that you use this command, ln-s, and then point at whatever your zones.c is located at, so that when you make changes to zones.c to pass the tests, it's going to be reflected in every directory that you have this in. It's going to be this, they're all pointing at the same file. Yeah?
Can we use our make file to copy zones.c into each of those directories? And further, can we use the make file, like make our, you know how there's a make clean? Can we, like I did this for the previous assignment, do a make submit so that it like updates the directory where that contains the folder of files that were eventually going to submit for the assignment?
Yeah. you're more than welcome to have any targets in your makefile that you want to do stuff like this. When the graders get your submission, they won't even have this folder inside of it. I'm going to delete these folders before the graders get your submission so that they have their own copies of the identical test suite. Because I want to make sure that just in case someone's unintentionally edited the test suite, that we're using the one that I've published as the actual one that runs their code.
I was just wondering because we've been graded on
The makefile is, does your makefile build your code? That's the assessment that's being made here. Yeah. The assessment here is, does your makefile build your zones.o in the directory that you've submitted? Yeah, that's all we're looking for here. Yeah. If you want to do really cool stuff with make, please be my guest. I'm very happy to see that. Yeah. So this test suite is test 1. And this test suite is kind of like a happy path test. What it does is it makes a zone. The first thing it does is it makes a zone. And then it goes through and it allocates a bunch of increasing sizes of allocations. So this notation, we're going to talk about this operator today, this greater than operator, less than. We're going to talk about this less than operator today. This is the left shift operator. What this does is it's taking I plus 3, whatever that is, and it's bit shifting. So it's moving all the bits over just a little bit. It's taking 1 and it's bit shifting it by I plus 3. So it's moving all the bits over just by a little bit. Shifting things, specifically shifting 1 by whatever, is raising it to powers of 2. So it's kind of like it becomes 2 and then 4 and then 8 and then 16. And so this allocation list here is going through the process of making allocations that are 2 and then 4 and then 8 and then 16 and then all the way up to 512 before it stops. Then it's doing zdump, and then it's going to calculate that the block size reported for each of those pointers is equal to what was allocated in the first place. So because we're doing this in a specific order, we can go through in the same order and then check to see that the block size that we requested to be allocated is the same as what was allocated. Then we're going through the process of releasing all of those things and then destroying the zone at the end. Here, we're going through the process of allocating 1 byte over and over and over again. And then we are writing over everything. So this function here, memset, is filling the entire buffer with A's initially after that 1 byte allocation. This is kind of breaking that whole array index out of bounds thing. I know how big the buffer is, so I'm just filling the entire thing up with the letter A, even though only 1 byte has been allocated. Again, you can't do anything about that. You can't stop me as the user of this library from overwriting stuff past the end. But I am guaranteeing here that I'm only going to write up to the number of bytes that are in your zone. So I'm just going to fill up the whole zone with the same letter. And then I'm going through and doing a bunch of 1 byte allocations, and I'm checking to see that each of those 1 byte allocations has been zeroed. So I'm filling the whole thing up with A, and then checking to see after I do the subsequent allocations that you've done the zeroing of blocks after I request them to be allocated. And so what should result at the end here is that there's just 1 A at the beginning now, because the second allocation that I did was to immediately zero it out. So it's the null byte, it's the end of the string. Then I'm going through the process of setting these all to B and A. So I'm just swapping them back and forth. I'm checking to see that the whole string is 16 bytes of A, B, A, B, A, B. And then I'm releasing every other one. Thank you so much for that idea. Thank you so much for that idea. I'm releasing every other one, and then I'm trying to allocate 2 bytes. And even though there's 8 bytes free, I shouldn't be able to allocate 2 bytes because there isn't 2 contiguous bytes free. There's just 1 byte in between each thing. The last part here is that I'm checking to see that the string is still the same. It shouldn't have been changed because I wasn't able to allocate 2 bytes. And then at the end of the processing, I'm printing stuff out. got a little extra message here at the bottom in case there are failed tests when you put your code into this, and this should be highlighted in like red with a white, red background with a white foreground. In each of these directories, you're going to see that there's a README file that describes approximately what the test does. It tells you how to compile it and what the compilation process does, but there's always going to be a make file in each of these. And then all the test cases will have this expected output and expected Valgrind. So if I run my test here, this is the expected output. And what I should be able to do is if I cat expected output here, I should see the same thing. I can use this program called diff to see if expected output and the actual run of this are the same. So I can redirect this to be something like myoutput.txt. I can do diff on expected output and my output. And these are okay to be different because the addresses that you get are going to be different than what my addresses are when you call malloc. But the rest of it, the part where it's saying pass and fail, that should all be the same. The other thing that's in this directory is the expected output from Valgrind. Whoops, I'm going to run expected output Valgrind. When I run my program with Valgrind, this is the output that I get from Valgrind. And the way that I'm running my code with output is I'm saying Valgrind -- log file equals whatever the name of the file is that I want. So my Valgrind.txt and then the name of the program itself. So the name of the program itself says just run that program. And now there's a file in here that's called my Valgrind.txt, and it will just print out whatever Valgrind would have otherwise printed out. So it puts everything in a file as opposed to putting it into standard output. All right. So are there any questions about this first test suite or in general about the structure of what I'm giving to you? Straightforward. OK. All right, cool. The second test suite is some more tests that are just kind of using a test kind of setup for zones, but this time it's making multiple zones as opposed to just making one zone. This one goes through the process of allocating 4 separate zones that are each slightly bigger than the last. And then it fills up each of those zones in this setup function by just filling it with stuff. So each of them are going to get filled with something. We dump them all out, and then we're going through the process of confirming that the contents of each of these zones is what we put in it in the first place. Then we're going through the process of destroying zones that have been created and then making sure that the other zones are unchanged. Every zone that you get back from make zone should be a completely distinct zone. It's a different object, so you don't have things overlapping. And that's effectively what this test is doing, is making sure that all of the zones that you're creating on each call to make zone is going to be different from the other zones that you've got. Test 3 here is one more test of your base implementation of this zone structure, but this is the one that violates all of your assumptions. So in this case, the make file is going through the process of compiling your code with the dn debug flag. So this is the make file that's going to be used to run this test, and it's turning all of your assertions off in your code. The expected output here, so I'm going to run that ln command again. The expected output here is that your code will pass. It's going to print everything out, and it's not going to segfault. I'll be honest, when I wrote this test for myself, I had to stop and change things in my zones implementation twice because I got seg faults as I was doing it. I'm not immune to this. I'm not immune to this. I had to fix stuff based on my own tests. But this is the output that I'm expecting you to get. Test 4, you may recognize. Test 4 is the implementation of the stack from assignment 2, but it's using zones instead of malloc and free, because I can't leave this assignment without having it be something about brackets and bracket matching. Like, I got to stick it in there somewhere. And so the colors, this is the bonus implementation, should work. It should work. This is the expected output from that. It's not different from what assignment 3 was. The difference here is in stack, where in the make stack function, we're doing a malloc for the stack structure, but then for the nodes, we're actually putting them all inside of a zone structure. And the idea here is that when we get to destroy stack, we can just destroy the zone and then free the stack. We don't have to go through and release every node that's been allocated within the list. And this is what we're trying to accomplish with this whole zone-based memory management thing. So the output from this should be effectively identical to what you had in assignment 2. And then the last test case is the one that I am the most proud of. This is a game that I've made that uses a library here that's called curses. I don't know what the history behind this library being called curses is. It might be something about jokes about dark magic and stuff like that related to working with terminals. I don't really know where that comes from. But if I run the game, my name is Franklin, then what we get is something that looks like this. And I'm going to make this just a little bit smaller. So the @ symbol up there, that's you, that's your player. And these $signs that are laying all over this room are items that you can pick up. You use your arrows to move around. So I'm moving around the room right now. And for each of the items that you pick up, your score changes just a little bit. And the hashtags or octothorpes or number sign or whatever you want to call them, these are doors. And as you leave the room, it reinitializes the room and it fills it with new items. And so every time I leave a door in this room, I'm getting a new list of items that are being assigned, and it's all kind of random. And, oh, I thought that was an applause. Thank you. It's not. Yeah. You can press D for some debug information here to print out some extra stuff, like where you are in the room and then where the doors are located in each of the walls. And then to exit this so that you don't leak memory from your implementation, you must exit with X. So that ends the game. This game is it's 500 lines long. It's 500 lines of code long. I spent an embarrassing amount of time writing this code. So I hope it pleases all of you to see this. This is what I'm imagining when I'm imagining Link's Awakening. You know, you move from one screen to the next. And as we go through the process of, okay, 500 lines, but like my coding is like there's big blocks of comments and stuff on each thing. So it's maybe not quite 500 lines. The idea here is that we've got this function that's called initialize room, and we've got this function that's called destroy room. My main function here doesn't have a lot in it. So I initialize the game. These function calls here are for curses. So they're setting things up so that it basically takes over the whole terminal for me. And then this part is unimplemented, but I might add it back later. The gameplay itself is handled entirely within this while loop. So while this is running, while you haven't pressed the X button, it does 3 steps. It displays the room, it prints everything out. It reads input, so it reads like pressing the arrow keys on your keyboard, and then it does pick up items. Handling input and pick up items both change the state of the room and the player. Display room does not change any state. Everything is constant in the context of that function. So if I go down here to display room, way down here to display room, this function has a couple of preconditions that are both just invariants of the object. Then we go through the process of calling some functions that are part of the curses library. So move 0, 0 takes your cursor and puts it to the top left corner of the terminal. And then this add.ch function just adds a character. It starts printing stuff out based on where you are right now. We're going through the process of basically adding the walls, adding items. We're checking to see if there's an item at a specific location, trying to see where the player is right now and adding them to the screen. And then we're printing some stuff out at the bottom here, which is just that extra information. So the first part is doing this all character by character, and then there's these print W functions that will print strings like printf does, but it does it in the context of this print, in this curses setup. The initialize room function here is one that will go through the process of making a zone for the room itself. So it's the room and all items that are in the room. We're allocating space for the room in the zone, and then we're going through the process, once we do that, of generating a bunch of random items here, and we're allocating those all inside the room. When you exit a room, so in the handle input function here, when you do this, we just destroy the room and then we initialize another room. So as you leave through one of those doors, we destroy and then initialize, and the destroy room function just destroys the zone. That's it. It just destroys the entire zone and then initializes a new one inside of a new zone. So we're not having to worry about how many items we placed on the screen. We just fill it up with stuff and then destroy the entire zone at the end. If you're feeling bored after this course is over and you want to make something with this, please let me know that you have made something with this, but you're more than welcome to take my code and do that. Because I know you're all going to be itching to keep programming in C after this course. Yeah, yeah. But that's it. So I invite you to play. There's no point to this game, obviously. It's like get a high score, but the rooms never end. They just keep going forever. There is no expected output file in this directory because there is no expected output. Like, it should work and it shouldn't crash. That's what this game should look like. But there is expected output for Valgrind. I'm going to show you this because of this part here. Curses leaks memory. The curses library leaks memory. And what I want you to see here is that all of the leaks that it's able to find are being called from this display room function, and they are all located ultimately in libncurses.so.whatever. These are not leaks in my code. They're not leaks in your code. These specific ones. If I go down to the bottom here and I skip past all of these display room related things, there are still reachable chunks here, but I'm expecting that you would get this kind of output from the game. The leaks that it reports should not be in zones.o. They should not be in zones.o. The only place where the leaks are okay for this one is going to be in the ncurses library. That is out of our control. We can't change the ncurses library to not leak memory. Any questions about the test suite? Yeah. When I originally planned this, I was going to put hidden items in it, yes, but I didn't. So add an Easter egg and send it back to me, and I'll see if I can find it. Yeah, yeah. Any other questions? +1 bonus mark. How would you report that to me? Like, send me a hash code of something? Like, +1 bonus point for the highest score. Yeah, if you can overflow long, then you have wasted hours of your life, and you will get yeah. Okay, so yeah. So there's Valgrind that does memory checking, and that's what this expected output is. The other one is called Callgrind. So that's a special tool inside of Valgrind that we can run. When we run Valgrind by default, it's running the tool called memcheck, and that's testing to see if there's any leaks in the code. If we change the tool to Callgrind, then it starts to do performance analysis for us, and it tells us how long each function took to run. Oh gosh. So if I did that, so I'm going to say Valgrind log file equals tool equals Callgrind. And then I'm going to run game. And I got to stop this for a second. I need to say log file Callgrind.txt, because otherwise it's going to mess with the whole display. So if I run through this a little bit, and then I hit X to exit, and I do kcachegrind on callgrind.out 752, just pick the biggest one here. I mean, it's going to be kind of a mess because there's a bunch of other stuff that's happening here. So in this function, well, I guess it's not as much as I thought it was. It's calling display room and item at. If I call main, it's calling all this other stuff. It's not reporting stuff in ncurses, I guess. So yeah. So this is just doing performance analysis, and it's not doing the memory check stuff. All right. This is 5 hours of my life that I'm not getting back. Yeah. But I did have fun doing it. I did actually have fun doing it. So yeah. Anyway. It looks like a nice game. What do you mean? It's just like an @ symbol and $signs. What kind of a game is that? Okay, I'm really digressing here, but there's this game called NetHack, if you've ever heard of this. NetHack is a roguelike game, and I don't know if you've ever heard the name roguelike before, but NetHack looks like this on the screen. So it has fancier graphics than I've got, in that it doesn't use like blank spaces, but it is using things like the @ symbol for the character, and then all these other things, so like this colored parenthesis, the %, the asterisk, these are just different kinds of items that are located around the room. Their rooms are also not just hard-coded to be constrained at 20 by 20 characters. They're, I believe they are procedurally generated. They're just generated at runtime. And instead of going from kind of like down and northeast, southwest into different rooms that way, you're kind of descending into a tower or climbing up a tower. I think in this one, you're climbing up a tower. So you're moving up. And then as you're going through, you can kind of see that the walls here, this is a wall, but this area has just been unexplored so far. So as you go through here, it's also doing like light calculations to try and see which way light would go to determine whether it should reveal this part of the room to you or not. Then there's also monsters and stuff, so you'll have to do battles and encounter them. Yeah. If you want to build this from my code, let me know. But yeah, I thought about going this far, and then I like bailed out pretty fast. It would take me more than 5 hours. This is decades of work. This game has been around for decades. I don't know. Like we're looking here at 2011, 1994, like decades. We're talking about decades worth of work. Yeah. Oh, yeah.
Is it the cursive library? Thing every time so it doesn't print out?
Yeah. So the curses library here basically takes over the entire terminal, and it starts to use special codes to do things like, as I'm moving around, like it's redrawing the entire room every single time, but it's starting at the top, and it's just like letting me basically go to coordinates on the terminal as opposed to just printing and then printing and printing and being able to clear lines. But we could accomplish this with, again, arcane magic related to terminals, but why do that when somebody else has done it for you? Yeah. Okay. That was a digression. By the end of today's lecture, what I'm hoping for you to be able to do is, given an existing solution, identify and explain where the use of appropriate data structures, algorithms, and/or techniques, such as caching and lookup tables, provide better paths to optimization than low-level code. Last week, we were looking at identifying the place where we might need to make these changes. Today, I specifically want to look at this one here, where the use of appropriate data structures provides better paths to optimization than low-level code. I'm going to show you some I'm going to show you some Java code that is code that I wrote. I prepared it as an example for this class, but the case that I'm showing you in this code is something that I wrote as a person that worked at a place and put into production. And we'll get to it. We'll get to it. But this is an example of something that I really did in real life in a real job. The other thing that I want to do, and we may not get to this based on the time that we have left, but is continuing to describe the benefits of modularity and use simple metrics to specify the degree of independence, such as coupling and cohesion. Last week, when we looked at these two concepts, we were looking at these from the perspective of these really abstract images and like trains and tracks and stuff like that. Today, I want to look at this, or today or tomorrow, I want to look at this from this perspective of code specifically. So I want to take measurements of coupling and I want to take measurements of cohesion about examples of code, and then think about how we can change it to separate things into modules to increase cohesion and reduce coupling. So we did some profiling stuff last week. And what I want to talk about to begin with today is optimizing for space. And this is really related to that whole idea of data structures. When we're thinking about code, when we're writing stuff, we are often using a lot more space than we actually need to represent the information that we're representing. There's an example here that I can think of sparse data sets. And if you think all the way back to Comp 1020, the canonical example of this is that you're using partially filled arrays. You allocate a bunch of space, but you only use a little bit of it. Other kinds of examples are you allocate an entire array and you use just parts of it scattered throughout, but then the rest of it is kind of used and it's unable to be used. In the test cases that we've got for our zones, an example of this is we allocate one single byte and release every other byte, and we cannot use this space because it's kind of spread around all over the place. Another place that we're using way more space than we need is when we just have high volumes of data. There's a couple of examples that I'll go through with high volumes of data. The first one is video. I would like you all to do some imagination here. Imagine that you have a 4K video that's playing at 60 frames per second. 4K has a resolution of this many pixels. I want you to imagine this, and I want you to think about Each pixel takes 3 bytes to encode. So we have more bytes than this in video, but let's simplify it. We've got red, and we've got green, and we've got blue. If you look really, really closely at your monitor, you might see red and green and blue as like subparts of those dots that are on your screen. We can imagine that each pixel has 3 bytes for each of these, and the different bytes will represent the intensity of each of these colors. So it'll be from 0 to 255. If we have this setup, I'd like you to just do some simple arithmetic. Pop your calculator open on your machine, or if you can do this in your head, great, cool. Try to think about how much data per second this might be. I'm going to give you 10 seconds to do this. I'm going to pop open my calculator here. I'm going to go back to the basic view here. So we have 3820 by 2160 pixels times. So in total, we've got 8,251,200 pixels. Each of those pixels takes 3 bytes. So we've got about 24 megabytes of space per frame, and we're playing 60 frames per second. So if I divide this by 1024, right now we have a number of bytes. This is now kilobytes. This is megabytes. This is gigabytes. So for 1 second of video with this setup, we've got about 1 and like a little bit less than 0.5 gigabytes of video per second. Yes, 1.38 gigabytes per second. Yes, good. That is the correct response, yes. Most modern disks cannot keep up with that. Some can, yes, some can, but they can't keep up with it. And if they can keep up with it, you're not going to be able to store that much data because 50 gigabyte Blu-rays can only hold like 50 seconds of video or less for that kind of volume. If we were watching 4K videos on our phone on whatever network provider you're on, it's going to be a really like super stuttery video watching experience because you're trying to watch a gigabyte of video every single second. It's bananas. So we got to do something, and the solution here to using way too much space for these really, really high volumes of data is to use an approach that's called compression. Compression is one way to save space for very big things. Compression at a really high level goes through the process of analyzing the data that you're giving to this compression algorithm to try and find data that is redundant. So redundant here means that it's either not useful in the data, it's data that's there, but it's not actually useful, or it's the same data that's kind of copied over and over and over again within that high volume of data. There's 2 types of compression. There's lossless compression algorithms and there's loss-E compression algorithms. Lossless compression is I'm going to take the input that I've got and I'm going to reduce the size of the input. I'm going to try to reduce the size of the input, but I'm not going to lose any information in this thing that I've got. If I take this compressed file, I get a file, I run it through a compression algorithm, and then I decompress it. I take it back out again. I should have 2 identical files. Lossless means I don't lose any information. I put a bunch of data into it. It maybe makes it smaller. I take that smaller maybe file, and I take it out, and I get exactly the same thing that I put in after it. So if we were thinking about this in terms of code, if we have this void pointer that points at something that's really big, if I pass it to a function that's called compress and I get a pointer to some other data, if I pass that same pointer, that compressed function, that compressed data to another function that's called decompress, the contents of x and z should be identical. There should be no data loss. We should have input to one function, output from the other function, and we just get the same thing back again. This is lossless. We have not lost any information in this. Examples of lossless compression schemes are zip and unzip. You put files into a zip file and you extract them and you get identical files out again, but the overall file size is smaller than what the directory structure looks like. When you use hand-in, for example, it's compressing the files that you've submitted. So you might have noticed that the number of bytes it reports are smaller than the file sizes that you have on disk because it's compressing it. When I uncompress it or decompress it, I get your files back in their entirety. I don't lose any information through that process. Another example of a lossless compression scheme for audio is called FLAC. This is called the Free Lossless Audio Codec. When you take music from a CD or from a music studio and you encode it with this algorithm, when you play it back, you're getting the identical data that was put into it in the first place. You're getting everything back. You're not losing any information. Lossy compression is that we're reducing the size of input by, yes, compressing it in some of the same ways as lossless compression algorithms, but we're reducing the input mainly by discarding a bunch of information. We're throwing a bunch of stuff away. The stuff that we're throwing away is usually things that I'm going to like double air quote here as it's not important data. This means things like I cannot actually see this. So if there's data in a photo that's in the ultraviolet or infrared part of the spectrum, I can't see that. You can't see it. Shrimp might be able to see it, but they're not looking at these pictures. So we can get rid of that information. We don't need to put it in this compressed thing. In audio files, above a certain frequency, humans cannot hear. Your dog might be able to hear it, but I can't hear it. So we can get rid of that information from the file. We can just chop it off and throw it away. When we take that data that we've compressed and we put it through our decompression algorithm, we're going to get something that's really close to what we put in, and it may be indistinguishable to us as humans, but it's not identical to what we were able to put in. So in this case, we've got the data that we've got, we're passing it into our compress function, we're decompressing it, and if we did make this comparison, it's going to be different, but our eyes and ears are not able to perceive a difference. Examples of this are JPEG. So I don't know what JPEG stands for, but JPEG is an image format. When you take a picture with your phone, that raw sensor data is going through this compression algorithm before it gets stored as a file on your device. And it's throwing away a bunch of extra information about light levels and intensity. MP3 is going through the process of taking audio files and chopping it off at a certain frequency. We can't hear it, so don't bother storing it. The difference in size between FLAC and MP3 is an order of magnitude. So like a FLAC file is going to be 20 megs and an MP3 might be just 3 or 4 megabytes in size. They're vastly different. H.264 is a video compression scheme, and when you are bored, when you have 10 free minutes, this is an old article, but it is a great article. I really like this. And this whole idea of we've got 1.3 gigabytes of space, I've increased the numbers here to represent modern technology, 4K as opposed to 1080p, but we can do the same kind of approach here. And what this does is it takes you through this idea of what H.264 is doing. One example of an idea that's done in video compression schemes like this is that you have these frames that are really close to each other, but the amount of data that changes between frame 1 and frame 2 is not that much. They're mostly the same. So you can take mostly the same images and basically just store a difference of what was had from frame 1. And storing just the difference is significantly less volume than storing the entire thing all over again. I'm going to give you out some strips of paper right now. I wasn't confident that we were going to get to this, but I want you to think about this, and I'd like to see what you report back to me, and I will report back to you next class. We're making a trade-off here. What are we trading off when we're doing compression? I'm just going to give a bunch of these out, and I'm going to ask you to pass them down, please. And then if you need a pen, oh gosh, these are all just crumpled up, terrible messes. I'm sorry.
You know what AVIF is?
AVIF? Yeah, actually, I don't know. Is that a video compression or an image compression? Thanks. H.264 is not proprietary to Apple. This is the encoding that's used on Blu-ray. It's a proprietary video encoding scheme, but it's not to Apple. There's like a consortium of companies that were involved in developing it. If you need a pen, I've got pens and stuff. Stick your hand up. I'll give you like 10 more seconds. And if you don't finish writing down in the next 10 seconds, that's okay. Just finish before you leave, and then drop it off at the front with me before you leave today. Okay. Again, if you're not finished, that's okay. Please feel free to give it to me after class. Compression can involve a lot of difficult math. Like we're talking like Calc 2 and onward level math for doing stuff like this. It can involve a lot of tough math and a lot of additional theory. We have offered compression courses in this department. One of them is called coding theory. And this is a course that's almost always only ever offered in a graduate level course in a computer science program. And the other one that we offer is information theory courses. They are also in grad studies. These are not typically things that we'll offer to undergraduate students. There was a topics course that we just had in compression, but it's at the 4,000 level. And it has some pretty mega requirements in terms of the math courses that you need to get into that course. So if compression involves tough math to do things like, I want to take these videos and squish the hell out of them so that they fit into the disk that I've got, what can we do? Compression's out of scope, so what can we do? We need to take a look kind of at a different level for what we're trying to accomplish. As opposed to compressing stuff, my idea, and I think a good idea in general here, is that we need to change how we are representing the data in the first place to accomplish reducing the amount of space that we are taking for the code that we're writing. The way that I'm thinking about changing how we represent the data is to use a data structure that only uses the space that it needs. Up until the end of Comp 1020, this is the data structure that you were using to represent some collection of strings. By default, this would be the choice that you would make because this was the only tool that you had access to. If you wanted to initialize an array of strings, you would initialize an array of strings with a fixed size, and then you would leave all of these extra spaces as empty. You'd have this idea of this partially filled array, and null would be the marker that says this is where the data ends. But each of these spaces that's not being used is space that we cannot use for anything else in the system that we've got running. So a better choice for this would be to use a linked list structure. I'm only going to allocate as much as I need at the time right now. When I create my list, I have one element in it, and it points at null. As I add new things to this list, I'm going to add new nodes to the list, and this may take more space in the long term, but if I have lower needs initially for data, I'm going to choose a data structure that uses something a little bit less. Generally, if we're thinking about specific ways of implementing something with arrays, a data structure that's going to use less space than an array for the same data structure are things like lists, linked lists, and binary search trees. If we have matrices, a list of lists, a sparse matrix, is a better data structure to use than just allocating the entire chunk of memory as an array and using that thing. Many of you have taken Comp 2140 already, and some of you are taking Comp 2140 right now. These are the data structures that you're seeing there. If you're in honors, you may be taking Comp 3170 later and see even more of these data structures there. Here is a code sample. I'm actually going to pop up the code that's complete in my terminal here. This code is already on the course webpage as search.java. So if you're interested in taking a look at this, please download this to your local system. What this code does at the beginning is it initializes two collections. A collection here is a data type. It's an abstract data type that says, I have many of this thing, and I can iterate over them. I can start iterating at one end, and I can get to the other end. But there's no order stated. There's no element 0 in this thing. There's no element 10. There's just a big bag of items that I have, and I can go through them all, but what order I get them back in is not stated by the abstract data type. I can add things to this. I can check to see if a thing is in there, but I can't ask other questions like, what's at element 10? All this is there's a bag of things that I have. This code goes through the process of adding all of the words that are in the dictionary. On a Linux system, this file, user shared dict words, is a dictionary of English words. There's other dictionaries that are on systems often, but this one has a bunch of English words in it. This uses Scanner to just go through that whole file and add all of the dictionary words to this collection that's called dictionary. There's another collection that's called words. This collection here is going to be the words that I'm going to search for. And what this does is it iterates over the collection of words that I'm searching for, and it asks if the dictionary contains those words. If it does contain those words, then I'm going to print out that word was found in the dictionary. I want you to take 30 seconds right now, and I want you to think about why this code might be slow. I want you to explicitly ignore lines 14 through 24. These lines are not part of the example that we're talking about right now, but the other lines that are in here that are on the screen are part of what we're talking about right now. I don't need an answer, but just take 30 seconds to think about what might be causing this to be slow. Okay. I'm going to pop open another terminal to the side here, and I'm going to leave this code up on the screen. I'm going to change into this directory. I'm going to compile this, and I'm going to run it. I'm going to also use a command that's called time. We did profiling with a profiler. We used gprof and we used colgrind and valgrind to do profiling for us. These are very fine-grained profiling tools. They will tell us how long a function takes in the code that we're profiling. Time is a command that tells us how long the whole program took, and that's what it tells us. It cannot give us fine-grained information like how much time is spent in each function, but this is what we're going to use for this right now. So if I run this, it took about 239 milliseconds to run. That doesn't seem like it's a very long program. That seems reasonable. I'm going to add to words the same word. I'm just going to copy and paste that line. I'm going to compile it, and I'm going to run it again. And it took about 231 milliseconds, slightly faster. I'm going to copy and paste this line again, and I'm going to compile it, and I'm going to run it again. And I'm looking at the wrong number. I'm looking at the user time here, and it's about the same. I'm still going to copy and paste this a bunch more times. And I'm going to compile this, and I'm going to run it. And I'm going to compile it, and I'm going to run it. And I'm going to compile it by adding this 1,000 times. And I'm going to run this. And it's starting to take a second to run. I'm going to add this 10,000 times. And now it's taking 3 seconds to run. I'm going to change this code to be a word that is not an English word. Zoop is, I think we can all agree that this is not an English word. And all I really did was change the word I was looking for. Our abstract data type here is collection. I want to be able to add things to my collection. And in this case, I'm really just testing to see, does my collection contain something? I'm going to make one change to this. I'm going to change like technically 2 words, but it's stitched together as one single word. I'm going to change this to hash set instead of linked list. And I'm going to go up here. I'm going to import hash set. And I know that Visual Studio Code would do this for me, and I still just live my life this way anyway. Yes. That's a fair question. If I put star here instead of naming all these things, does it take more space? This is only relevant for the compilation phase. It doesn't actually get used when the program is running anymore. So I'm going to compile this, and I'm going to run it one more time, and now it's basically instant. I've gone from taking 11 seconds to do this down to 200 millis again. 656 milliseconds. This is a real example. This is code that I wrote and I put on a web server in a workplace that did this. Not exactly this. I was searching for something called motifs, which is related to genetic information. But I was doing this. I had a collection and I was doing just this contains check. Is this thing in the collection or not? With an array list here, when I do contains, what kind of a search do we have to do on an array of potentially unordered data? Linear search. The big O of linear search is on the beat of after the beat of 3, please. 1, 2, 3, n. So for the word zoop here, it is not in this dictionary. And when I search for it 10,000 times, I have to search through every entry in the dictionary to find out, no, it's not there. My abstract data type, my ADT collection, gives me the ability to ask this question, and the data structure that I'm using to implement it right now, an array list, is an array. It's a list of arrays. Like it basically fills up an array, and then it allocates a new node in the list. And then it fills up that array, and then it allocates a new node in the list. And it's still doing a linear search. If I change this to be a hash set instead of an array list, and I use this data structure to implement my abstract data type of collection, my contains now, and I know that you're doing hash tables right now in 2140, yes? Or you just finished them? Yeah? My hash set is making a hash table, and it's hashing the word zoop, and it's just doing a lookup in that array and saying, no, there's nothing there. And that's all a constant time lookup. So we're switching from doing on every time we need to check to see if this thing is contained within that to o1 for our hash lookup as opposed to the linear search. Are there any questions about that? The big goal here is don't try to work faster. So don't try to go to low-level code. Don't try to re-implement an array list in C to get some perceived speed up. Do less work in the first place. Switch your data structure to one that's going to do less work for the kinds of questions that we're asking. Do less work. Don't do work faster. Any questions? We're good? Okay. I'm completely serious. This was on a web server. There were people running it, and like this was from a paper that I published, and this was code that was running on this web server, and people were using it, and it would just sit there and spin forever. And it would spin and spin, and it would take 20 minutes to click the submit button, and that's not unusual for the kind of data that we're working with genetic data, because it's big, like lots of data. But I did this exact change. And it went from taking 11 minutes to like 5 seconds. And I was a grad student at the time. I was a grad student. Yeah, I was a grad student. I don't know what that says about me. I don't know what that says about me. It says that we're not all immune to this. We're going to come back to this tomorrow. But changing our data structure should kind of always be the first approach. In this case, the data structure that I'm looking at here doesn't necessarily change the amount of space that's being used. We still have to put that whole thing in there. But we are going to at least change the time requirements for the implementation that we've got here. In terms of squeezing out the last few bits, this is where we're going to get to thinking about manipulating bits in C. And we will talk about this tomorrow. I'm going to talk about this tomorrow in 2 contexts. I'm going to talk about this tomorrow in terms of the way that the Game Boy Advance represents colors for pixels. That's not specifically what I want to talk about with the Game Boy Advance this week, but I also want to say, please lower your expectations for what we will do with the Game Boy Advance stuff. Lower them much lower than you think you need to lower them to. We're not going to be doing very much. I want to show you how you can get your environment set up and point you at documentation for libraries and do the minimalist example possible to get a ROM running in a Game Boy Advance emulator. That's where we're getting. We're going to look at this in that context with the Game Boy Advance. I also want to look at this in the context of compression. So thinking about how I take genetic data. So genetic data and genomes they're very poorly implemented as text files for the most part, and they're using the letters A, C, G, and T, and they're using the ASCII characters A, C, G, and T, but we can fit that into a much smaller space. So we'll talk about both of those examples tomorrow. And then we'll do the coupling and cohesion thing tomorrow as well. So at this point, you should be able to identify places where things are kind of running slowly, and then explain where the appropriate use of data structures can help solve the problem that we've got. Algorithms and techniques such as caching and lookup tables, we may look at those, but I'm really, really mostly interested right now in terms of data structures. Switching from an array list to hash set, given what we're trying to ask of this abstract data type, changed the performance of what we were looking at. Describe the benefits of modularity and use simple metrics to specify the degree of independence, such as coupling and cohesion. We will look at tomorrow. Thank you all for coming, and I will see you tomorrow. Bye, everyone.